Today we're going to look into electron transport chain and oxidative phosphorylation. Just want to also announce that most of the videos that will be given to you for this semester is in fact those that already been made into videos from last semester during the time of lockdown. Therefore, you might have some information that can be considered obsolete or not relevant, which is more relevant for last semester rather than meant for this semester. So please take note of that, and I will make announcements from time to time to inform you what is relevant for this semester, which is for you. So before we go into an overview of how these carriers operate in order to generate ATP, which involve another carrier which is not been shown here is complex 5 or ATP synthase. But here, as the title reflect, it only covers electron transport chain. So in terms of these complexes, you have complex 1, complex 2, complex 3, and complex 4. Of course, later, which is separated from this electron transport chain, is complex 5. Basically, these complexes will carry the electron up to oxygen, and oxygen will be made into water molecules. It starts off, it can be started off with explaining about NADH losing its high energy electron, or it can be also started by explaining about the release of FADH2 once succinate is converted to fumarate. That is the one of the steps of citric acid cycle, which is directly connected with complex 2 based on succinate dehydrogenase. So you have at NADH release of high energy electron. It goes to complex 1, to complex Q, coenzyme Q, sorry, to complex 3, cytochrome C, and then complex 4. Then the energy in the high energy electron will become lower and lower until it meets up with oxygen and become water molecule. Uh, when the NADH loses high energy electron, it also accompanied with loss of hydrogen ion, and therefore a buildup of hydrogen ion takes place in the location itself. When talking about the FADH2, because of the succinate becoming fumarate, then complex 2 will cause it to lose high energy electron as well as hydrogen ion, and therefore this higher high energy electron also goes through the circuit of electron carriers, that is from complex 2 to coenzyme Q, complex 3, cytochrome C, and then followed by complex 4 until oxygen. So this is the circuit for the FADH2 electron, while the circuit for NADH electron was referred earlier. Another interesting thing about this slide, it also explains why NADH once been converted to ATP, you get 3 ATPs, while FADH2 you only get 2 ATP. This is evidently shown by the Gibbs free energy. You can see here for FADH2 is minus 152 kilojoule per mole, therefore far lesser than that of NADH Gibbs free energy of minus 220 kilojoule. That's why you get 2 ATPs in FADH2 oxidation, while NADH oxidation you get 3 ATP. This is a interesting chemiosmotic model that's been suggested by the guy, a picture I put there, Peter Michel, in the early 1960s. When he wrote the journal and provided this chemiosmotic model, the contemporary scientists at that time were not happy with him because they had a different understanding about how ATP is made in the electron transport chain. For them, electron transport chain only exists, it does not couple with oxidative phosphorylation. According to them, due to the electron traveling from, say, complex 1 to that of oxygen through carriers, it will eventually cause making of ATP similar like substrate level phosphorylation. Uh, there is no involvement of the complex 5 as been suggested by Peter Michel. But his model eventually was accepted because many evidence came forward that supports his chemiosmotic model. So to make the story short, basically when NADH and also FADH2 loses its electron and goes through these electron carriers, it will also cause the hydrogen ion to come to the inner intermembrane space. Intermembrane space is between inner membrane and outer membrane. And this hydrogen ion comes from the mitochondrial matrix, where it is achieves ability to come from mitochondrial matrix to the intermembrane space due to the electron traveling. Because electron travel, they have high energy, and this high energy is given to something like a pump that brings the hydrogen ion from the matrix to the intermembrane space. Eventually, in the intermembrane space, there will be high gradient of hydrogen ion. It is referred as proton motive force, and nowhere else to go. It will try to go back to matrix, and the only route is through the complex 5, where it shoots from the intermembrane space into the mitochondrial matrix. And due to the FO and F1 component of the ATP synthase or complex 5, eventually ATP is generated. This slide basically gives you an overview of what happens it also shows you in terms of the structure of the cell that you have cytoplasma, mitochondrial matrix, you have the outer membrane, inner membrane space, the carriers that is found in the inner membrane itself that helps in accomplishing the buildup of ATP. It's the same as previous slides, except here you have the complexes shown in much more detailed manner. You have the FMN, FAD, cytochrome Q, cytochrome B, C, all the content of the complexes. For example, you have the electron released by the NADH. As it travels, it becomes like a pump to take the energy from the high energy electron and then push the proton hydrogen ion from the matrix of the cytoplasm of the mitochondria towards the inner membrane space, and then the high hydrogen ion or proton motif then comes through the ATP synthase or complex 5 in order to generate ATP. And also don't forget the low energy electron will help to convert the oxygen to become water molecule altogether. So this is just to generalize what happens in terms of electron transport chain and combined with oxidative phosphorylation.